This video covers sum to infinity for an infinite geometric series. Now, QCAA subject matter is understand the limiting behavior as n approaches infinity of the terms in a geometric sequence and its dependence on the value of the common ratio. And we need to establish and use the formula S infinity, so the sum to infinity equals T1 over 1 minus R when R is between 1 and -1. So let's consider the sequence 1 over 3, 1 over 9, 1 over 27, 1 over 81. You should see that that's geometric. To get from our first term to our next term, we times by 1 over 3. Then we times by 1 over 3, etc. So our R is 1 over 3 and our first term is also 1 over 3. Now, if we did plug into our full formula for a sequence, a geometric sequence, knowing that our formula is S of n equals T of 1 R to the n minus 1 over R minus 1. Okay, for the ninth, to go up to the ninth term, the sum of the first 9 terms, it would be approximately 0.499975. Okay, now if you looked at the sum of the first 20 terms, it's approximately 0.4999999986. So what you should be seeing here is that as the number of terms increases, our sum looks like it's approaching 0.5. So we can say this is approximately 0.5 and this is approximately 0.5. So it doesn't matter how many terms I keep adding, that sum is not it's never going to reach 0.5. Okay, and that's because our R value is between 1 and -1. So we're timesing by a small amount. So our small amount is getting smaller and smaller and smaller each time. So each term is getting smaller and smaller and smaller such that it has no impact on the total sum. So if I had 1 and my R was a half, I'd times it by a half and I'd get half. Then I'd times it by a half again and I'd get a quarter. Times it by a half again, I get 1 over 8. So each time these terms are getting smaller and smaller and smaller, such that the extra term doesn't really have an impact on the sum. And that's where we get to our infinite geometric sequence. So our sum as n approaches infinity. Okay, so if R is between -1 and 1, then the infinite geometric series T1 plus T1 times R plus T1 times R squared, etc., is convergent. So it goes towards a certain number. And the sum of infinity is given by S of infinity equals T1 over 1 minus R. Okay, so let's look at it for this example. Our sum to infinity is going to be T1 is 1/3 over 1 minus R, which was a third. So that's 1/3 divided by 2/3. Okay, so 1/3 divided by 2/3 equals a half. If we looked at this one here, sum to infinity is going to be, our first term is 1 over 1 minus our R, which is a half. So that's going to be 1 divided by a half, which is going to be 2. Let's look at the sum of our first 4 terms by just adding them. So we've got 1 plus a half plus a quarter plus an eighth. 1.875. Okay, if we went one more term times by a half, that'd be 1 over 16. So S5 would be add 1 over 16 and we get 1.9375. So you can see that it's converging on that value of 2. So let's look at some more examples. The first one, find the sum of to infinity of the series 1/2 plus 1/4 plus 1/8. So first of all, what's our r? We're timesing by a half. So we know it's geometric. Our T1, our first term, is a half, and our r is also a half. Our formula, by the way, is on your formula sheet, so make sure you can locate that. So it's a half divided by 1 minus a half, which is a half divided by a half, which is 1. The next one, a square has a side length of 40 centimetres. A copy of the square is made so that the area is 80% of the original. The process is repeated so that each time the area of the new square is 80% of the previous one. If the process is repeated indefinitely, find the total area of the squares. Okay, so when you're seeing this, total area of all the squares, you should be thinking of sum. When you see the word indefinitely, you should be thinking infinity or to infinity. So let's think about the area of the square. It has a side length of 40, so it's going to be 40 squared is 1600. So that's what it's starting off at. Now this 1600 is reducing by 80% each time. So we're timesing by 0.8. So it's geometric. Our first term is 1600 and our r is 0.8. So our r is less than 1. So we can use the sum to infinity. Write our formula, plug in our information. So 1600 over 1 minus 0.8, which is 1600 divided by 0.2, which is 8,000 centimetres squared. So therefore, total area of the squares is 8,000 centimetres squared. Our last example, express the recurring decimal of 0.32 recurring as a ratio of 2 integers. Now we're using the sum to infinity to do this. I know you've done these previously without using the sum to infinity. We're using the sum to infinity. So the way to do it, I've got 0.32 and the 32 is recurring. Okay, so essentially that's 0.32 plus 0.0032 plus 0.000032, and then that would keep going. So to get from this term to this term, I'm timesing by 1 over 100. To get from this term to this term, I'm timesing by 1 over 100. So it's geometric. Our T1 is 0.32 and our R is 1 over 100. Now, if you can't see where that 1 over 100 comes from, remember it's the second term divided by the first term. So if I wanted to do this by hand, just say this was in a tech-free paper, which it could be, what I do is I want to make the top one whole, like a whole number. So I need to times that by 1, 2, 3, 4, 10,000. So I do the same to the bottom. And I end up with 32 over 3200. Then you should be able to say 32 into 32 is 1. 32 into 3,200 is 100. So it's 1 over 100. Now, R is less than 100. Sorry, less than 100. I've got 100 in my head. R is less than 1. So I can use S infinity. So let's write our formula and plug in. 0.32 over 1 minus 1 over 100, which is 0.01. I'm leaving it as 1 minus 0.01 because then I have decimals top and bottom, and you'll see what I mean by that. So I've got 0.32 at the top. 1 minus 0.01 is 0.99. And you can see why I went to decimals. So if I times the top by 100, do the same to the bottom, I have 32 over 99. Now, if you go to your calculators to check it, 32 divided by 99 is 0.32 recurring.